Alright, here we are again, live from Ms. Malinowski's house. Fabulous. You can see I've got some fabulous paintings behind me. Those are all done courtesy of my sister. Aside from this here of my dog. That's a puzzle. One of those fun things where you send in a picture and they give you a puzzle back. Yeah, that's my boobies. Okay, anyways, writing exponential models. So again, this last time they gave you the equation. You had to explain what the pieces mean. This time they're giving you the situation and you need to turn that into one of these exponential functions. So we are still going to be using that notorious formula from previous, the y equals your initial value times 1 plus or minus, depending if it is a situation involving growth or decay, your percentage divided by 100, because that's what we do to percents to convert them into decimals, raised to the exponent of t, which stands for time, whatever that given situation is. So that percentage representing your growth or your decay. And yeah, that's really all I got to say. That initial value, that's starting when time is 0. Some people like to think that time's the first year when you're starting, but it is not. When you're starting off, time is 0 when you're starting. Ugh. All right, so let's jump right into this. Example uno, a flock of ducks growing. So this is a growth. I'm going to be using the plus. Growing by 6% each year. Time is going to be measured in years then, I'm guessing. Starts with a population of 68. So there is my initial value. Create an exponential function to model the number of ducks. Okay, that's some good spelling there. Ducks after t number of years. Then, there's a then. We love those thens. 2 things, 2 questions, 2 things to do. How many ducks will there be after 10 years? All right, so I'm going to just jump right into using that formula and just start filling in the pieces. So, I'm going to use y equals initial value of 68. 1, I'm using the plus sign, not the minus, because it's growth, and we already decided that. 6 divided by 100, and I'm going to raise that because first I need a generic equation that I can use that I can plug in any number of years. So I'm going to plug the t in for that first and make that generic equation. Then I will use it to figure out how many are there after 10 years. So looking at my equation here, I'm just going to do a little bit of simplifying. That's going to turn into 1 in 600ths after you do the 6 divided by 100 and add that to the 1. Keep going, and I'm just going to take one more step because right now I technically have this written as an equation and not in a function because it's not f of x or f of t. So I'm just going to change this into f of t is equal to 68 1.06 to the t time. Then I can use that function. Here's the then part. The then. I'm going to use that function to find out how many there will be after 10 years. So f of 10 being the new number of years, 68 1.06 raised to the 10th power. It is okay if you don't have f of 10 here and you just have, y equals instead, if that's, makes more sense to you. And then jumping into the calculator to do math because we work smarter here, not harder. 1.06 caret to the 10th. Okay, so 121.7776. We're talking about a number of ducks, so I do not have a decimal worth of ducks. That would be rounded to the nearest whole number, would be 122 ducks after 10 years. which, just a quick makes sense check, it does make sense because the population of ducks was increasing, so I am ending up with a higher number than the 68 that we originally started with. So yeah, yes. Stay tuned for example number 2.